And let me see if I gave you guys, I think I gave everybody permission to share.
Perfect, perfect. All right, you guys see my screen okay? Or not yet? Okay. Okay, so let's begin with these 5 questions, and if there's additional questions, we just answer them as I go. I think for this time, I'm just gonna be talking as I go through the questions, just so you guys can get my opinion on the questions. If you guys have any clarifying questions, feel free to ask me. Do you guys want me to ask you guys rhetorical questions, or do you guys just want me to move forward?
You can ask rhetorical questions.
All right, we'll go to, we'll see how it goes then. Perfect. All right. In homework 5, you have from homework 5, we have question 11.51.
Yeah.
All right. So in 11.51, it asks, oh wait, sorry, hold on. The form of this guy is I'm gonna have the right hand side be just some overall concepts that you can take away. Okay.
Yeah, let me start. Did I start there? Okay, I did.
Yes, you did. Yes, you did. All right. 11.51. In analogy with the figure in circuit 11.89, a student constructs a stage depicted in 11.91, but mistakenly uses an NMOS for M3 instead of a PMOS. Okay. Assuming lambda is equal to 0. So assuming lambda equals 0, that is to say that R naught goes to infinity. Using Miller's theorem, compute the poles of the circuit. Okay. So from this guy, we need to, oh God, okay, this is a lot. We need to draw out all the capacitances, I think.
Yeah.
All right, I'm gonna draw all 4 of them out. So every single FET has 4 capacitors. You have one from gate C, from gate to drain, And you also have the capacitance from gate to source. Then you also have the capacitance from source to bulk. And you also have the capacitance, from a drain to bulk. Is this correct understanding?
Yes.
All right, and we subindex them all 3 to pay respect to the fact that it came from M3.
Yep.
Okay. We do similar drawings for the remaining. FETs. So this is C source bulk 2, C drain bulk 2, C gate drain 2, and C gate source 2. And then we also have that of M1. So I draw the 4 capacitors.
When you draw, do you use your mouse to draw, or do you have like a pencil?
Oh, this is I've definitely been true to you guys with just a mouse.
Jesus, man, that's pretty good.
Ah, I'm fucking with you. Yeah, of course it's a pen.
I was like, damn. I was
No,
doing
dude.
Jamboard and it was taking me forever. I was like, how the hell does Eric do this with mouse?
No. Goddamn.
Yeah.
Of course I have a pen. You think? Oh, yeah. This is. Otherwise, there's no chance I have any way to do
Yeah.
this.
I'm like,
Gate,
so precise.
gate source, gate drain 2. 1. Jesus. Gate drain 1, gate source 1, source bulk 1, drain bulk 1, gate drain 1. Okay, yes.
Yeah.
Here are the 4. Okay. Then from here, we can make a from here, we can make a we could eliminate some of these guys out.
Yeah.
Okay. We can eliminate out Mr. Oh, hello. Oh,
Yeah, okay.
What's up, bro?
good. Yo, okay. So from here, we got tons of things that we can eliminate out. So for example, we could things that are both AC shorted. So for example, VDD is now AC shorted. V bulk is AC shorted. Bias 1, bias 2 are AC shorted. So I can AC short these
Question,
guys,
Eric.
AC short these guys, and AC short these guys. Yes, sorry.
Are you gonna AC sort first and then draw the parasitic
the capacitors? Or are
Yeah,
you gonna draw
doesn't
the?
matter. Order doesn't matter because I haven't
Okay.
made the simplifications yet.
Okay, sounds good.
Okay. All right. So yeah, so now you can eliminate capacitors that are just terminated with the same AC ground from both sides. For example, the drain bulk has ground on the right and ground on the left. Therefore, this guy doesn't matter.
Also,
Gate drain, yes, sorry.
yeah, that one, right? The CGD3.
CGD3 is completely out as well. Correct.
And wouldn't it
CS1.
CGS3 as well because it's grounded on the left side and also grounded on the never mind. Yep.
Ah, see, be careful. No, they are not correct.
CSB1.
But CSB1
Yes.
for sure you could
Yep.
eliminate because it's grounded on both sides.
Yep, that is all I
But
believe.
yeah, and yeah, everything else pretty much stays there. Okay, so now we eliminate out the parameters that we don't like. So now we go to the next step here, which is now we can combine. We can now combine, or actually here. We can kind of combine capacitors. So from here, I can say, let me do this. I have how many capacitors, or sorry, I actually don't need this. How many capacitors total do I need? Let's just start writing them out. Okay. So I have,
You can
let's
combine
say,
them because of the node, right? Like the
yeah, because the capacitors are in parallel.
yeah, okay.
For
Yeah, we
example,
can.
so I'm just gonna call this guy the V. Let's start with V C out or we could let's do C out. Okay, so for C out, this guy involves CDB2 to ground,
Yeah.
plus CGD2 to ground,
Mhm.
and those are the only two capacitors that touch the V out net. Would you guys agree?
Yeah.
All right, so these guys are now accounted. Okay, now I want to do a different capacitor. Let's call this guy here the drain of M. Let's call this C drain of M1. Is that okay?
Mhm.
Yeah.
Yeah.
The drain of M1, okay? And for this guy,
CGS3.
sorry. Let me call this
Let's call that V, like VX or like CX.
I'll call it VD1, the voltage on the drain of M1. Okay, so it corresponds to a capacitor. So this guy has CGS3 plus CSB3. It also
CS2.
CSB2 plus CGS2, right?
Yep.
Yeah.
And CGD1 times 1 minus 1 over A, I believe.
Okay. Well, hold on. Let me just take this guy first. Plus CDB1, right?
GDB.
Yep.
And then I have the CGD1, but it's not to ground. Notice all these other capacitors were touching the node and to ground. Touching the node and to ground. So those you just add straight in. But for this guy, it is Millard. So I know I can break this capacitor into two capacitors, each to ground, right?
Oh, okay.
So I'm going to do CGD1 and times some, oopsie, CGD1, and this guy's at the output of M1.
Yeah.
So this should be, what is it?
1 minus 1 over A.
1 over 1.
Yeah, 1 over 1 minus.
1 over 1 minus A. Is this right? Sorry, I don't recall what my proofs were. Let me see.
Is it 1? I think I put like 1 minus A.
1 minus 1 over A. Is that the same?
Sorry. I understand where I went wrong. I see.
It's 1 minus 1 over in A
Yeah,
of M1 though.
Yeah,
You can say A1 actually, right?
Yeah.
Let's say A1. Yes.
Yes.
Okay.
All right, and that's CGD. Okay, now that's these guys. So all these guys are now accounted for. And then it's just one more left, right?
C in.
C in. Let's call it C. Well, it's not technically C in. It's on the gate of M1. So I'm just going to call it CG1. And this guy has CGS1, right?
Yes.
Plus CGD1 times
1 minus A1.
1 minus A1. Yes?
Yeah.
Yes.
All right, I totally agree with you guys.
Let's find the gain of A1 or M1.
Let's find the gain of this guy. So we need to find what A1 is. Okay.
Mhm.
So A1 is going to be equal to
Negative GM.
Oh, hold on. I'm just gonna take this original circuit because this is all that matters to find A1. Okay, so A1 here is A1's the gain from here to here, not from here to here, okay? It's the gain across it's the gain across this device.
So
That's-
wait, really quick, 1 minus 1A1, is that just, that's standard, right? From capacitor, is that what
That's when you go to the output side. The
Okay.
out when you drive
The output has that, and the input has the other one.
Okay,
yes, if you have a gain of A and you have a device, a capacitor across it,
And the Miller,
Miller implies that you can do this.
you got two capacitors, one an input and one an output, and one has the form of 1 minus 1 over A, and the other one.
oh, that's right, I remember that. I had that
Okay.
like midterm 1. Makes sense.
Yep. So that's
And to
this-
remember that is specifically for capacitor, that expression, but actually it's
yeah.
different. If you're gonna call that the impedance,
If
then
I call it some Z, then it's a little bit backwards. For capacitance, it happens to look this cleanly.
correct.
Yeah. The general Miller form for impedance is yeah, it's like the inverse of this, but yes. Yes. I think I had it on previous notes where I proved it.
Yes.
Yeah,
Okay. So for A1, we gotta find what A1 is, and it's the notice that A is defined to be the gain between the two terminals of the capacitor. So look at the two terminals of the capacitor, it's here and here. So the
Oh.
gain is only from here to here.
Yep.
Not from here to here. It's not from here to V out. It's not from V in to here. It's not from V in to here. It's
Mhm.
strictly from this node to this node, which are the two nodes across of the capacitor.
Yeah.
That's
Gain
the definition of
between-
A1.
Yep.
Okay. So if we go this, we have A1 is equal to it's just a common source, it's just a common source amplifier of M1.
Correct.
So I go down to my handy dandy cheat sheet, which I hope has been helpful.
instrumentally, yeah.
It is the cheat code to this whole class.
Question, Eric, for this
Yes.
cheat sheet that you made for us, is
Yes.
there a way to simplify this table to like what, because this includes a channel length modulation, right? Assuming, yeah, how could we make another table like this without it?
Just for the simplicity of the math.
If you get rid of RO, oh,
Like I was trying to like recreate the table just by like crossing out RO, but then in some cases,
no, you cannot cross that. No,
Yeah.
you cannot cross out RO.
yeah,
I mean, it's algebra, so you can do whatever the hell you want. But here,
Yeah.
I understand what you're asking me for. You're asking me.
I don't want to be rude, like ask for too much, but if you,
I know what you're asking. You guys are asking.
one.
You're asking for everything. I get it. I get it.
we,
I get it.
we,
No, I feel.
if you're
I'm
up
picking
dinner,
up.
you know, I really appreciate this.
No. I'm picking up what you're putting down. It's okay. It's okay. You want RD? RO goes to infinity. This RO, you divide. You can't have infinity over infinity. So you have to divide top and bottom by RO. So this guy's gonna be RS times divide top and bottom by RO. So this is gonna be 1 over RO plus GM. Okay.
Yeah.
Okay, so you have that over GM. This RO goes to infinity. So here you have RD in parallel with RD RS 1 over GM. Okay.
Mhm.
And then from this guy, you want to probably execute this is a little bit ugly. So let's just execute out the division. So you're gonna have RD times RD over RS plus 1 over GM divided by RD plus RD over RS times 1 over GM. For this guy, I would probably
I think
multiply.
that's fair enough up to there. Like,
It's not the prettiest. It's not the prettiest.
no, but
but-
they look, I mean, better than the
You can for sure factor out the RD. Like you could cancel out RD at the top and
Right.
RD out of each of these guys. So now you have negative GM RD over RS times 1 over GM over 1 plus 1 over RS GM. And then from here, you probably want to, you could multiply through by this GM, and then you multiply top and bottom by RS. So you get this.
Okay, that's
You get this. Yeah. Okay. Is that better?
yeah.
It better be.
Yeah,
Yes.
better be right. Yeah, this is what you get. Something feels odd about it, but I think that's correct.
Common source play that we just did.
I think so. I think that's what it simplifies down to. Oopsie. But honestly,
I will check later.
yeah.
What you did, and I can just
Oh wait, hold on. Did you want that proof?
no. I wrote it down.
Okay. Yeah, I'm saying there you go. That's the guy.
Yeah.
Here I already gave it to you.
Oh yeah, that's true.
Okay. I mean
It's there, yeah.
It's been there the whole time.
Yeah.
Okay. And this bottom guy, if RO goes to infinity, I pray that you guys can simplify. This bottom one's meant for RO goes to infinity.
Yeah.
And this one's supposed to be GMRD.
Yep.
And boom, there's your table. So the only weird one is this one.
Ooh, thank you.
All right.
Appreciate it.
Yeah. They've been there. They've been there. All right, we're going back to the problem. All right, so here, if I'm going to still keep to this form, so this is GM1, RO1, RO1, RO1. Okay, and there's no RS. RS is 0.
Mhm.
So this is negative GM1 RD from 1, which is the drain looking up. Parallel infinity and divide by RS. RS is 0, so this is divided by 0, so all this goes out. So you have GMRD, where this goes to infinity and this goes to infinity. So you're fine.
We need
Okay,
to
so then the question is, yes, sorry?
we need to find what RD1 is now.
Correct. Now you're motivated to find what RD1 is. Okay, RD1 is the input impedance looking up into 2 devices.
Mhm.
You can look into the source of M3 and the source of M2. So I need the impedance of 2 sources. So we go down to the cheat sheet. We go into the input impedance looking into a source is here. Okay. And I want this to be the source. I want this guy to be, oh, I don't need that. I want this guy to be the source of M2 and the source of in parallel, right?
Mhm.
These two paths are in parallel with each other.
Yeah.
So I need the source of M3 and the source of M2.
Correct.
Okay.
Mhm.
So this guy is equal to RO3 is infinity. Oh, sorry. Okay, let's do this. RD3 is 0. So it's RO3 plus 0 divided by 1 plus GM3 RO3, right?
Mhm.
And then on the right-hand side, RO2, actually, you know what? It doesn't actually matter, but RO2 plus RD is a real RD divided by 1 plus GM2 RO2. If I just divide top and bottom by their ROs respectively, I just have 1 over RO3 plus GM3.
Yeah.
And on the right-hand side, I have 1 plus RD over RO2 divided by 1 over RO2 plus GM2. But if all the ROs go to infinity, this goes to 0, this goes to 0, this goes to 0. So you should just get 1 over GM3 in parallel with 1 over GM2. You guys have any questions here? Or you guys okay with this?
Yes.
Yeah, I'm okay with it.
All right, that's RD. So once you have RD, you have this, and then you have this. So in other words, this A1 becomes 1 plus GM1, 1 over GM2, but 2 parallel 1 over GM3. Yes?
Yeah.
That's this term. And similarly here with the inverse. Okay?
Yeah.
And then the poles, the question is, where are the poles? You need to find the equivalent resistances with these guys. So we need R out. R out is the resistance seen by this guy looking out, right?
Mhm.
If I look at R out, it's RD in parallel with the impedance looking into the drain of M2, right?
Mhm.
And if I look into the drain of M2, if I look into the drain of M2, it's this, but R is infinity, so it's infinity. Yes?
Yeah.
So this is just RD. And if it's in parallel with infinity, basically, which is equal to just RD. Okay, see RD1 is going to be the impedance looking from the drain, from RD1 looking up into here, and down into here, right?
Mhm.
But if I look up into here and up into here, that's already eerily similar to this work here, right?
See.
Okay, so I could just steal that from what our previous experience was. If you have this net and I'm looking to the penis, it's this guy in parallel with this guy in parallel with this guy. But looking down into M1, that guy's just infinity. So it's just 1 over GM3, GM3, GM2.
That makes more sense.
Then lastly, the resistance on the gate of 1 is to the left is infinity and to the right is RG. Okay, so the poles of the circuit is just 1 over RC. 1 over RC, 1 over RC. Is there any questions there?
No, that makes sense. We have it written out.
Okay. There's your 3 poles.
Okay.
Do you guys have any questions?
Not with this question, but can we find the gain of the circuit?
Okay, wait, hold on. Let me check our work real quick. Okay, they said that you have a pole at RG1. Okay, RG, so this guy's RG, and then you have CG1. CG1 is CS1 plus 1 minus A CGD1. Yes?
Yeah.
So this guy is confirmed. Next guy is pole 2, which they say associates with GM2 plus GM3. Oh, that's just this guy. That's just GM2. That's just this guy. If you guys did the parallel, if you did the parallel, this is equal to GM2 plus GM3. Okay. Or sorry, 1 over GM2, GM3. Sorry. So this guy appears on the top. And then the capacitance here is CGS3, CSB3, CSB2, CGS2, which is confirmed here. And then CDB1, good. And CGD1, 1 over 1 minus A. So yes, matched. Yes? You guys okay with pole 2? Match.
Yeah.
It matches with this and this.
Yeah.
Last one is this one, which is just RD. And then RD is paired with CDB2 and CGD2, which it says here. So the only question is, what is A? And they said A is negative GM1 times these 2 in parallel. Okay. You guys have any questions?
Looks perfect.
It is perfect. Now, the follow-up question was, what is the gain of the circuit? Wait, do you want the high frequency gain? Sorry, are you looking for the DC gain, or you're looking for its actual transfer function?
DC gain.
Oh, the DC gain. Okay. Then here, okay, here. Let me do this then. I'm gonna do this really quickly on the side. Is that okay?
Yeah.
Okay. If you want to find the gain of the circuit, then first from here to here is nothing because this is just an infinite voltage divider. There is a capacitance here, but he said ignore the capacitor, so it's open circuit. So if this side's V in, this other side is technically V, or the gain from here to V gate 1, then here to V drain 1, and then to V out. From here to here, right, is just a gain of 1. VG1 for every V in is just equal to 1 in DC.
Great.
Okay, so these are just the same voltage DC wise. Then VGD1 to VD1 is common source amplifier, which we found to be negative GM1 times 1 over GM3 parallel 1 over GM2. Okay, now you could take the step from here to here. Now you can take the last step from here to here, which is a common gate configuration. So we just go to common gate. Common gate. Okay, which is just GMRD. Okay.
Yep.
So we come up here, and now you want the V out as a function of VD1, which is just negative, which is just GM positive. It's not negative. GM2 RD, which is RD.
Okay.
Okay, and then the total gain from V out from V in, it's equal to, algebraically, it's just VG1 times V in is one transfer function times VG1 times VD1 times VD1 V out. And the nice thing about transfer function is that all these terms effectively cancel, and I get V out over V in trivially. Or I can multiply each of the transfer functions together. And this is a 1. This is a negative GM1, blah, 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 blah. And the last guy. Yes?
Excuse me.
Easy. And this guy's GM2RD. Okay, multiply these 3 together, and you're done.
Okay, makes sense. Yep.
Okay, there we go. That's that question. Is there any other questions about that question? Or are we good here?
We're good.
Yeah, we're good.
Very nice.
Excuse me.
Bless you. Okay. Next question. Okay. Figure 14.35 shows a CMOS realization of a push-pull stage. Sketch the input-output characteristic of the circuit. Determine the small signal voltage gain for the positive. Determine the small signal voltage for the positive and negative inputs outside of the dead zone. Okay, this is now a very large signal approach to this. So what do I mean by that? We need a grid. Okay, there's a grid. Okay. Okay, so from this grid, so this guy is actually, it's not really asking for large signal, it's not really asking for small signal, it's asking you to kind of see how 2 FETs work together. This is the first time you guys would do a large signal analysis with 2 MOSFETs. That's the key difference.
Yeah.
That you now have 2 MOSFETs that are co-working together in the same circuit, and they're asking what's the large signal behavior. That's why this circuit is a bit weird. So, remember that a MOSFET, recall that you have 3 regions. You have cutoff, you have triode,
Saturation.
and you have saturation. Correct. And cutoff is denoted when VGS minus VTH is less than 0.
Yeah.
Okay, less than or equal, or let's say less than or equal to whatever, less than 0, or equal to whatever. I'll just put it there. Actually, no, I won't. This guy's VGS minus VTH is greater than 0 for both of these. But not only is VGS minus VTH, both have to be greater than 0 for both of these guys. But in the case of triode, VGS minus VTH is also greater than VDS. Meanwhile, here it's less than VDS. Okay.
I see.
That is for the NMOS, correct?
For the NMOS. And
So
then you could
opposite.
put absolute values everywhere if you want the other way. Yeah, you could just put a ton of absolute values. It's like the raw, just think about the raw magnitude of the way that you want to go beyond on, quote unquote.
Okay.
Yeah. Okay. So here you can see a gate source, and here I can see a gate source. Yes.
Mm.
So here's another gate source, So when one of the FETs are on, the other FET, okay, so when is this top FET on, basically? So notice that VE and VCC assume to be plus and minus rails around ground, okay? So in the highest voltage, what's the highest voltage V out can be? Physically, like allowable from this circuit, what's the highest physical voltage V out is allowed to be?
Highest physical voltage to be CCC?
Yes, it can only be VCC. So you know this circuit is limited by some VCC, okay?
Mhm.
So here is VEE, and this is VCC, okay? You know it's limited by that. Okay, you cannot go higher, you cannot go lower, okay. Next question is that when V, and if this axis, oopsie. So this is the V out axis, and this is the V in axis. It's an input to output axis. When V in is 0 volts, let's say V in is 0 volts, the output will be by default what? You assume the output is centered at 0 first, because you see a resistor centers it to 0. So in other words, if M1 and M2 are off, what is V out?
Isn't it just like flatlined?
It's not, it has to be some defined voltage, and this resistor helps define that voltage. M1 and M2 are complete open circuits. So basically the only thing I have left is the circuit. So then the question is, what is the voltage on V out if this is your circuit?
A voltage drop across the resistor out. So
Yes, but if it's open circuit, there's no current can flow, so the voltage drop across is 0 volts. So therefore, what is V out?
0 volts.
It's 0 volts, it's ground. So you call this resistor a pull down resistor. It kind of centers it. If you didn't have that resistor, then it's impossible to solve the circuit because V out is just floating.
Okay.
Okay, so it basically RL just gives you a way to center the voltage or like reference the voltage to something at least.
Yeah.
Okay, so if V in is 0, suppose V out starts at 0. I need to be above the threshold voltage for M1 to turn on, and I need to be somehow below ground to turn on. V in has to go below ground to turn M2 on, because this is a PMOS. I need to bring this gate voltage down below the source. And for NMOS, I need to bring this voltage above the threshold to turn this guy on. Does that make sense?
Yeah, it does.
So if V in is 0, like assume the output starts off. In these circuits, I would strongly recommend you assume the output is just cut off. V in is 0.
So just based on those characteristics, you can just like draw the graph, right? Like right now, like so for PMOS, it would have to go down, right?
For PMOS to be on, V in has to go downwards, and at what point does it actually have a trigger? It triggers at when it goes to VTHP, right?
Yeah.
And before that, well, as this guy goes down, will the NMOS ever turn on?
No.
No.
Why? Because the NMOS requires a higher positive voltage above ground to turn on.
Yeah. So it'll just be flatlined. It'll be like 0.
Yes, it will be 0. The output will stay 0 because who's helping it stay 0? This resistor until this guy turns on.
I see.
And then this guy has some kind of gain, right?
Yeah.
Okay. And so here is, so there's, yeah. And then over here is some VTH from VTHN MOS. And this guy will stay on. And then it will go up. Okay? Until it, sorry, what's the question?
You said he will stay on. You meant to say he will stay off and then go on, right?
Yes, stays off and go on. So sorry. So in other words, in this middle regime, what is the status of M1 and what is the status of M2?
Both are off.
They're both
that's-
off.
Both are off. Correct. Over in this regime, what is happening?
M1 is on, M2 is off.
M1 is on, M2 is off. But also be careful. I fucked up when I do these lines because I can never exceed VCC. So it flatlines again here.
Okay.
Yes, does that make sense, guys?
Yeah, one off on.
Okay. And and what about over here? What about over here?
PMOS is on, and
PMOS is on and NMOS is on.
Okay.
Yeah,
And then over here is just straight up, it's just the thing hit rail. So not much you can do. Okay. Now, what is the slope of this red guy? So suppose this guy turns on and you're in saturation. What configuration is going from here to here?
Common drain.
What'd you say?
Common drain.
Common drain, which is also known as a source follower. Why is it called a source follower? Because the gain is approximately
2 source.
the source follower. What is the gain of a source follower or a source follower or a common drain? If R naught goes to infinity, which is ideal, yes, Josh, you were correct. The gain approaches approximately 1.
Yeah.
So that's why it's called a source follower has no voltage gain. So what's the slope? What's the slope for these two red lines approximately?
either 1.
Actually, they're both +1, right? Because they're both
Oh yeah,
positive.
yeah.
The both slopes are +1. That's correct for both of these scenarios. So then you might ask, what's the point of a source follower if it has no voltage gain? Don't look at the voltage. Remember, in electrical engineering, we have two things. Look at how much input current flows into this guy. None. You guys agree? I in is 0.
Yeah.
Look at how much I out goes. It's a huge amount because you're channeling everything through these guys. So I out is huge. A source follower has no voltage gain, but it has massive current gain.
Okay.
This is the last stage that goes into your audio amplifiers. This is what drives your speakers. Like when you drive like 1,000-watt speakers, you have to have such a stage to actually push real current through your speaker load.
by that you mean you have to have like a PMOS and an NMOS, or you mean just in general you have to
Typically, you have a push-pull. Yeah, you have a source follower. You have a push-pull stage.
Okay.
Yeah. It's very common, but you see a problem in the center, your audio is going to sound like absolute garbage. So there are ways to fix this.
Yeah.
There are ways to fix this. Typically, what you do is you put like a diode or so here.
Can you also have the configuration to have only source follower rather than pull push stage?
You mean only have one and you have a resistor for the other?
Yes.
Yes, but your swing is smaller. This one you see how you almost have rail to rail swing. If you do this other guy, remember these circuits are only valid when you are in saturation. The purpose of this guy is trying to extend the range of saturation. The problem is that this is in saturation, this is in saturation. These guys are not, but unfortunately there's a gap between the two. So you have a nice wide range of rail to rail saturation. What do I mean by that? Because as soon as Vn goes below the threshold, you're off, right?
Yeah.
So, but if you go below the threshold, you want the bottom guy to turn on.
Right.
So in other words, when you guys say that one is on, it's actually in saturation. And you want to extend saturation because you always want at least one FET on.
Right.
And then that way you could extend your Vin can now. So right now for this circuit, Vin has to swing between here, right? And you have to bias the voltage. Imagine you had a circuit that was like this, though, right? Imagine Then VN can be zero centered, and you could swing as pretty wide and get massive current boost.
Yeah.
So that's like the dream. So you're building up towards that dream.
Okay.
What you're saying is correct, but you now have to introduce bias circuitry that puts you here. VN has to be DC biased to like, I don't know, like 1 volt. Okay. Do you want to carry like a 1 volt battery with you? Does every single speaker you own have a 1 volt battery sitting inside it? No, hopefully not. But it has like typically, yeah, you want this plus minus rail centering. You definitely, and also it's very bad to put a DC bias on your load. Because think about this: when the input is 0, when the input's not doing anything, the output has what voltage across it?
Whatever DC is.
Yes, but suppose in this configuration, if both are off, what's the current flowing through RL? 0 amps, because V out is 0. There's no current flowing. And isn't that beautiful?
Yeah.
Because what does that mean when you're not playing music? It means you're drawing no power.
Right.
This type of stage is also a very efficient power amplifier. What you were going to propose was that if you put a DC bias, yes, technically you get the gain, but at the cost of a DC bias on V out, which means your speaker's always you're always drawing current through your speaker, and your speaker's going to burn actually. Because your speaker, it turns out your speakers rely on the motion of the speakers themselves. Like if you have a high power speaker, you rely on its own vibration of air to cool itself off.
I see.
If you guys try to put 1,000, if you try to put your speakers are only like 3 ohm or 4 ohm or
I
like
just
2 ohm
I just
speakers.
assumed it like create like a large reverberation or vibration just for noise. I never knew it like
No, it also is important for its own thermal characteristics too.
Mhm.
Your speaker wires will burn. That's why you do not want to ever apply a DC bias on a speaker.
Okay.
yeah. That's dope.
Got it.
All right. So this is a very efficient amp. You're trying to build a very efficient amplifier. Anyway, that's some context. But there are multiple reasons why you want this type of push-pull configuration. All right, sketch the. Oh, yeah, okay. It's called push-pull because each FET has its own. Like this guy pushes current in, and this guy pulls current out.
Yeah.
And that's kind of the idea. CMOS just means combined. Like you have an NMOS and a PMOS. That's what CMOS means. You have combined NMOS and PMOS in your circuitry, which you do. So this is technically a CMOS. This is technically an NMOS circuitry because you only have 3 NMOSs.
Yeah.
Okay. Sketch the input output characteristics. Yes, this is it. See, now you're okay. And then determine the small signal voltage gain for the positive and negative inputs outside the dead zone. So this is obviously the dead zone where everything's off, and the gain is about 1. Or technically, the gain is actually 1 plus GMRL over under GMRL. So the gain is slightly less than 1. Okay.
Mhm.
Okay, and that's the answer. Now they don't draw the rail to rail. I guess they assume VCC never rails, but yeah, there's your answer. You guys have any questions?
No, that was perfect.
Good.
That's definitely gonna be on the test.
Yes, it will be on the test. Okay, yeah, there you guys go. And you index them appropriately for M2 and M1. And here he puts absolute value. He puts an absolute because okay, different people have different definitions of VTP or VTHP, right? It could be plus or minus, I don't know.
I think you
So
said that
you say
earlier.
fuck it. Just say fuck it, just put an absolute value around it and put a negative sign because you know what's on the negative
I
side.
was say, didn't you say that earlier when you with the triode regions, you could basically just with the regions, you put absolute value if you want.
Yeah. You just put absolute value and a lot of things are solved, no matter what you do. If you don't know the sign of it, just put an absolute value and make your own sign
Yeah.
outside of it.
Yeah, he's definitely more conceptual than he is, like you got to know your algebra, calculus, and which is a good and a bad thing.
Yeah. It could be good and bad, but you do need to know how to check your mathematical work. All right. And is there any question on 4.13?
I'm good.
Okay. A student adventurously modifies a circuit in example, blah, 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 and assume lambda is 0. Fantastic. So lambda is 0. That means R naught goes to infinity. Okay. Prove by inspection that the feedback is positive. Okay. You guys need to know your concept of feedback. So for a feedback circuit, typically a negative feedback circuit, you have a plus terminal and a minus terminal. And the whole point of negative, and then typically what you do is this. You have an H, you have a G or something, and you come back, you have V out, and you have V in. And it's negative feedback because when, let's say, the way you prove negative feedback is that if V out goes up, you assume that this terminal here goes up. And if this guy increases, this terminal goes down, which then counteracts V out and goes down. So once I go through any perturbation in the loop, what you originally assumed gets counteracted. Notice I originally assumed 1 and I get slapped down with this final result. Does that make sense, guys?
Final result is your negative feedback.
Sorry, one more time.
In this case, right?
Sorry.
That final result will determine our feedback.
Yes, if let's say the final result, so I will show you guys systematically how to do this. So here's what we're gonna do. Start from the input, start labeling your nodes. So label this guy, let's call it 1. Or do you guys want to use letters or numbers? I don't care. Actually, let's use letters. Let's use letters because
we will have.
Because we're having numbers. All right, let's call this A. Now, which way do we get to the output? Which path do you think is the way for the forward loop? You go
From input to output.
Yeah, how to go from input to output? Because here I see a connection from output back to input. So one of these, I have 2 paths. Which path is the only valid path to the forward?
The top one, right? Isn't it?
Why?
Because you just said it yourself. It's feedback, so it'll.
No, but technically the forward path could be this way and I can loop back here, right?
That was actually like a question that we had last night when we were going.
Yes, it's a great question. It's a great question. If I draw a roundabout like this, right? Which way is the right way of the roundabout? Is it this way?
Somebody can say the other way be the right way, right?
Exactly. And I'm gonna tell you guys straight up, one way
Is it due to resistance?
One way is absolutely wrong. Sorry, what did you say?
Is it due to the resistance going upwards versus the bottom?
Nope.
Well, the resistance could be lower than the resistance of
Yes, correct. Here,
Yep.
I'll tell you this straight up.
transistor, so,
What is illegal to go as an input? What is illegal to go as an input? Which path? Which one of these terminals cannot be ever an input?
The drain.
Correct. You can never go into the drain. If you draw an arrow, so take a look if you went through RF, right? I can go into the source, but can a source ever go to the gate?
Nope.
Gates can never be the output.
Gate can never be the
Oh.
output.
You see
That
this?
was the conclusion we made yesterday. Gate cannot
Yes.
never be the output. But I was thinking maybe you can go inside the drain.
No, gates cannot. No, gates cannot be the output.
Yeah, I was pretty
we
sure
messed
you cannot
up.
output from the gate. That's why I was choosing that other path.
Yeah. Also, look at this. What the fuck are you about to do? Let's pretend you were okay with this, even though you're completely wrong. You go here this way. What's the problem? You go
You're
into the
gonna
drain. That's also completely wrong. Right?
Yeah.
You cannot do this jump. You cannot do this maneuver, and you cannot do this maneuver. These
Is
are
it
both
because of the
illegal.
arrows? Like the
So we essentially like like we were on the right path in terms of like why we couldn't go a certain way, but looking at the input and outputs from the table that you have is so much clearer.
Yeah, gates cannot be inputs.
Yeah.
Oh, sorry, cannot be outputs.
Gate cannot be outputs and drain cannot be inputs.
And
Yep.
drains cannot be inputs. That's the key takeaway here.
that just like cleared up so much. It's can.
Okay, but I hinted that to you guys from day one. This table comes from the fact that those rules were imposed very early on.
Yeah.
Yeah.
Okay, so why can't I go through this way? Because the source can be either way, so this is okay. But I will have to, for me to get back, if this is the forward path and this is the feedback path, notice how many things I butchered. Okay,
Yeah.
you cannot. That's why you have to go up this way.
But also generally, isn't it? If you do that, you're just looping back around. Isn't that just like dumb in percent?
No. Feedback requires you to loop back. That's the
Oh,
nature of
okay.
feedback.
Wait, so from this concept, so let's say we're talking about feedback now, feed forward, using this this idea that we cannot go into the gate and we cannot go into the drain, we cannot come out of the gate.
Mhm.
Can you would it be the same thing? Like
No, here. Let's go up. So from A, I will enter which path will I want to take? Up or down?
Up now.
Up. Okay. I go into the source and I go out of the.
drain?
Drain.
Is that legal?
Yep.
Of course it's legal.
That is a common amplifier.
Correct. So I will now label this. Now I'm here, and now I label B.
Mhm.
All right. Now I walk this way, and which way do I go? From gate into,
To source.
Source.
which is labeled V out already. That's great.
From there to A again. So yeah.
From here, I go, and then here I can go back to A. Yeah,
Yep.
that's legal. Any questions?
Nope.
Okay. So I have I in. So sorry. So I have A, B, C, and then I always label it back to A to B, B to C, C back to A. You guys agree?
Yep.
And here's what so this is how I would strongly recommend you guys do this. You walk through the path that the FETs allow you to, and you always make sure the first term and the last term are the same. And these are the voltages at these nodes. So assume the voltage on A goes, you guys want to choose up or down? I don't care.
Up.
Let's say it perturbs upwards,
Yeah.
right? And if you go through a common gate amplifier, does this go, is this inverting or not? So this from here to here is a common gate amplifier, which is inverting or non-inverting.
Uh-huh.
Non-inverting.
Right. So therefore, if A goes up, B goes
Up.
up. Then I go from B to C, which is what type of amplifier?
Common drain.
Common drain amplifier, source follower. And is that inverting or non-inverting?
Still up.
Non-inverting.
So C voltage would go up or down? Up.
Up,
And then if one side of the resistor goes up, the other side of the resistor should go
up also.
up. So so then you look at, then you only look at that. You look at the two.
So it's positive feedback.
Correct. That's it.
Oh my god, it's such crazy.
Yeah, my buddy was saying, the one that was just here and he left, he was saying if you look at the PMOS and the NMOS and the gain, if it's positive or negative, and that'll determine like if it's up or down.
Oh, I don't look, no, PMOS, NMOS doesn't matter. As soon as you know the gate, as long as you could label gate drain source and you know what type of configuration it is, it doesn't matter. PMOS or NMOS.
The only inverting stage will be common source.
Correct.
That's where while you are going up, the output will go down. Otherwise, everything goes up. And then
Yes.
you come to the first and the last node.
Does this make sense to y'all?
Perfectly.
All right, this is how, yeah, okay. That's it. Super easy. All right, that's how you do it. That's A. Part B, assuming RF is very large, breaking the loop at the gate of M2. Oh. Okay. Assume RF is very large, breaking the loop at the gate of M2. Okay. Calculate the loop gain and prove that the feedback is positive. Calculate the loop gain and prove calculate the loop gain. Okay, loop gain is just you just go through the loop. So choose a okay. So which side's the like you know how we just kind of did this
Yeah.
and you walked around? In this case, they want you to start where? They're saying please start at location
between M2 and
The
RD.
feedback?
B. They want you to start at location B. Right? And so which way does so it's like I pluck this guitar
Oh,
string.
I see. Yeah.
Which way does the signal go? To the left or to the right?
Going to the gate.
It has to go into the gate. So we're gonna call this my input, my quote unquote input, and this will be my output, and we're gonna see how it returns back.
So
Okay.
question real quick. If you had two transistors there, on one on each side, how would you pick which one to go into?
Has a transistor there, Jose. Right?
There is another transistor there. So which way do we go? Remember how we did from A to B to C? It's the only legal path.
We had a problem in which I believe we had two transistor gate to gate, and we broke it right in between. So then,
I doubt it. I'm gonna say I doubt that.
That'd be weird because gate can't be output, right?
Correct.
oh yeah, that's true. It was the same.
I doubt. Yeah, I'm gonna do a hard doubt there. Sorry. Not to say I don't believe you, but I don't believe you. So yeah. Okay. Does that make sense? And now we AC ground everything else, or should we AC analysis everything else? So VDD is this. I in is this is just an open circuit, right? Current sources become open circuits. And voltage, that doesn't matter anymore. Yes, you guys have any questions?
No.
And this is now B to C, back to A, and then back up. Yes?
Mhm.
Okay, so now they're saying solve for this transfer function. Does that kind of make sense?
Mhm.
All right, and hopefully if this number is positive, if the final result is positive, blah, 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 that means you have positive feedback. If it's negative, you have negative feedback. Does that make sense?
Yeah.
That's it. Okay. So B to C is what? VC from VB is a common what configuration?
B2C is common gate.
Common gate. So the source follower. So the and RO is supposed to be infinity. So this guy is going to be
Okay, so
this guy's going to be RGM RS2 over GM RS2 plus 1, correct?
Yes, 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 yes.
Okay. Meanwhile, RS2 is the resistance seen by the source, right? So what's the resistance seen by the source? So here I see RF in series with what?
series with the transistor M1 transistor.
Plus the impedance
Yeah.
into the source of M1, right? Right? Looking into the source of M1.
Yes.
So what's the source looking into the source of M1? Well, here's the thing. They said let RF be large. So if RF is large, I'm just going to assume this guy's negligible. Is that okay? Is that fair?
You're assuming what? It's large?
Yeah, it says assume RF is large.
Okay.
So no matter what the other guy is, he's going to be dominated by RF. Is that fair?
Yeah, totally fair.
Oh, VB is grounded. Yes, Josh, you were correct. This guy is also grounded. That's a fair point. Okay, so I'm going to assume RF is large. Okay, that's it. So that's the end of this guy. Now I go from VB. Now you need to go from VC to VA. VC to VA, right? So VC to VA, this is going to be a little bit tricky, but it's a voltage divider where I have RF plus RS1 and I choose RS1. Does that make sense?
Okay. Yeah.
Okay. So now I need RS1. Damn it. All right, hold on. Let me go. RS1. RS1. It's going to be this guy. Okay, RS1 is going to be this guy. R naught goes to infinity. R naught goes to infinity. Ignore this. R naught goes to infinity. So this is. It has an R. It does have an RD anyway. So I divide top and bottom by RO. So I have 1 plus. Oh, is this just 1 over GM?
Looks like it.
It is 1 over GM. All right, cool. So this is going to be R. So this is just 1 over GM1 divided by RF plus 1 over GM1. Any questions here about VC to VA? This guy's the bottom resistance and this guy's the top resistance. It's a voltage divider. Yes?
Yep.
Yeah, looks good.
All right, fantastic. Then I need to go from lastly I need to go from, I need to go to quote unquote V out. Maybe V out's a bad term. Maybe I'll call it VB. Maybe I'll call it V. Maybe I'll call it like
VN.
B prime or something. I don't know. Horrible name. What'd you say? V what?
Yeah. VN.
N? Like
Yeah, that's what we were using in class and in test.
like
V-
N? Like END?
No, and just a letter N.
N for Nancy.
N for Nant? Why?
I don't know.
Okay. All right. All right. N for Nant. Okay. Nancy. Goddamn. All right.
It's just expressive. It doesn't matter. Why do you hate that name though?
I don't know. There's no system. What's the rhyme or reason? What's the reason?
I don't know. During the lectures, we were using and and test. Like,
Yeah, but who the fuck is Nancy? All right,
I don't
anyway,
know.
keep going. Let's go A to B. Sorry, A to N. Jesus. Okay. This is a common gate amplifier. So, common gate, common gate, common gate. It's GMRD, positive. Okay. So it's positive GMRD, and this is GM1RD, and this RD is genuinely this RD. Okay. So the total gain, the loop gain, the loop gain is going to be this times this times this, which is going to be equal to, oh, this is GM2. It's going to be this
We have to solve
times
that.
this times this. Yes?
Yeah.
Yes. RS2 is RF.
Which is all positive. What'd you say?
RS2 is RF. That's what I said.
RS2? Oh, it's just RF. Oh, I see, I see. Okay, so we just make this RF. Technically, it's RF plus 1 over GM1, but they're saying, I don't know. All right, yeah, that's my answer. And it's all positive, therefore it's positive feedback.
Yep.
Yeah, it's positive feedback.
Yeah.
Okay.
Okay, which,
If in case there was a common source in any of the configuration, then it would be negative feedback, I believe, correct?
I don't know. Let's see what your book says. Okay, let's see. All right, sorry, what was your question? I just completely ignored it. What was your question?
Oh, it was another question. I was thinking if there was one common source
Yes, correct.
circuit,
Yes,
then I would make the closed loop gain to be negative, which will reflect that is a negative feedback amplifier.
correct. So assume the input is positive. I don't know, or sure, whatever. You could assume the current goes up, which means the voltage goes up. Yeah, assuming because you're assuming this resistance is positive.
Yeah,
Voltage goes up, then this guy goes up.
that's what you did for A, part A.
Yeah, kind of. I just said the voltage goes up. I didn't
Yeah,
say the
same
current
thing.
goes up, but it doesn't matter. You see,
Get the point.
you gotta just perturbate something in the loop. Positive feedback. This guy, the fuck.
Yeah,
VN. Oh, I see. VTVN. Huh? Okay.
labeled it different.
What is this? They said it's they assume this is just straight up one motherfucker. Oh, they assume RF is large. Oh, I see. So they're saying that this is about one. Okay. So here's your common source. This is this guy, right? This is the one. This is the one. This guy's about RF. Okay. They assume that RF dominates. So they're just saying, fuck this. Okay, fine. Okay. So 1 over RF. Great. And then you have, oh, wait, no. Sorry. They're saying RF just dominates. So this is just this bottom is just RF. Okay. And the
Yeah.
top here cancels out.
Okay.
And then they get
Oh,
RD.
Yeah.
So you have RD cancel. This guy dominates, and this guy is 1. Yes.
yeah.
Yeah.
Man, I really like the way you do it more. I wish you would have like done it more instead of like using shorthand. It makes more
Yeah.
sense. It's
Like
like
I said,
it's like chemistry, you know what I mean? When you're doing your stoichiometry.
yeah. This is it. This is why they call it transfer function. Every single time you multiply this guy, it's like a wild ride to a different point. Like
Yeah,
these are like, to me, they're like teleporters that let you go from point to point.
yeah.
And the algebra naturally supports you.
Correct.
Yeah. To me, this is why I always usually draw strict square brackets around these guys because this block is like a domino piece. If you multiply by the domino piece, you get transported differently.
Definitely.
Yeah.
Glad I made extra space on it's writing in here.
Yep. So this is a positive value. Therefore, it is the fuck. Oh my god, motherfucker. Okay. Oh, if this guy's positive, the loop gain is negative.
Oh, okay.
I don't know why. I don't. Fuck that. I'm not here to teach you guys that. I'm not. This is not an English class. You guys figure that shit out. I'm not here to figure that shit out. This is all I need to see.
Okay.
All right. If he wants to say loop gain positive is loop gain is actually negative version of this, I'm gonna fucking kill myself. I mean, Jesus.
Hey, English
Jesus.
is an important degree too.
What the fuck is he saying? This is negative, therefore it's positive? Huh? What is he saying?
It's greater than a negative number. It's the same thing as saying positive.
This thing's
Well,
greater
I'm-
than a negative number? Huh?
Loop gain is greater than the negative number or greater than 0. That's why it is a positive feedback.
No,
That's
no, no. This okay. Let's suppose this is true. Like this is the definition, right? So I'm going to put these two dots to emphasize it's a definition. It's saying that this is greater than 0. Isn't that like blatantly wrong?
That doesn't even make sense.
Yeah, that's what I'm saying.
If you're saying a negative number is greater than 0.
Yeah, that's what I'm saying. Listen,
I think he's trying to say when that thing is greater than 0, then that is a loop
I
gain.
just think he's saying you can write any of this crap and I'll give you points for it.
No, okay. I'm saying this makes no mathematical sense. Just write this and say positive feedback, or better yet, just say this and positive feedback.
Yeah.
All right. Well, anyways, we go next. Question 9. Find the input. Oh, wait, sorry. You guys have any questions about this? If you guys want to do another negative feedback one, feel free to bring up an example.
I think it all relates. You'll eventually run into another one.
No, well, I mean, I'm about to run out of questions, and these other questions ain't finding it. They're going to be input impedance and output impedance. That's the last 3 questions you asked for.
Yeah, there's a test too that Josh wanted to do that I think I sent it to you.
Oh, okay, I see. Input impedance 12.31, assuming RF is very large. Input impedance. So we go
Let's
this
do
way.
the feedback for this thing too.
What? This is the same problem though.
It's the same problem.
Oh, okay.
Yeah, they're the
Yeah,
same.
questions 9 and 10 from your homework reference. Question.
Oh, yeah.
Yeah.
Find the input impedance. I don't know. Okay, so I have 2 paths and they're in parallel. Okay, so I want the input impedance looking into the source of M1, Z in 1 source in parallel with RF plus something. Oh, plus the input impedance looking into the source of 2. Yeah? Okay. Z input impedance looking into 1. I'm pretty sure we just said that this is 1 over GM1 when R naught's infinity, right? And this guy's going to be 1 over GM3 when R naught's infinity. Okay. And we assume RF is large, so this is just RF. Okay, so it's just these 2 fuckers in parallel. Yeah? Any questions? Do I need to check my work? Okay, I'll check my work. Question 9. Find the input impedance. Ew. I see where I fucked up. All right, I am blatantly very wrong. I am sorry. I see where I've done. I see where I've messed up. When you guys have negative feedback, how do I explain this? Are you guys aware of this? Oh my god. Are you guys aware of this thing? Okay, when you guys do negative feedback, right? This is gonna be kind of a lecture, okay? So when you have negative feedback, you typically have an open loop, a forward loop gain, and a closed loop gain, right?
Mhm.
Okay. And in the presence of negative feedback, typically I am supposed to get this. This whole new system that I've made here, this whole new system has a new transfer function. And its transfer function, the total transfer function is equal to this. It's h of s, but it's divided by this term here.
1 plus
1 plus loop gain of s. Yes?
Yep.
1 plus loop gain of s, and the loop gain is defined to be everything inside this loop. Yes? H. So in this case, L of s is equal to h times g. Yes?
I remember that from last semester. Yeah.
Okay. So this is the definition of. So what do you see? If you didn't have feedback, I would have just had this circuit here. Without feedback, I would have just had V in, V out from H. Correct? This is my assumption. So before, what was my system? what was my V in to V out? It used to just be H. And with negative feedback, it's now H divided by this magical term. You guys agree?
Mhm.
This term, 1 plus L of S, and this look at this. This assumes negative feedback, right? This assumes negative feedback. So L of S is already assumed to be the negative feedback version. This term here is very magical. So what happens to my gain is that it gets reduced by this factor. You guys see that? Okay. Input impedances, depending on what type of input impedances, depends on what type of system you have. So in the case where I have an input current, do I want the input impedance to be high or low? What do you guys think?
Input impedance to
Wait,
be
repeat the
low
question again.
because you want every current to flow through the circuit, right?
Correct. So I want the input impedance to be low or high?
Low.
Low. So typically without negative feedback, my input impedance needed to be low. So now my new input impedance, closed loop, is going to be what? It's going to be my input impedance open loop.
Okay.
And I'm going to make it, and for me to be better, it's going to be smaller or bigger.
You want to make it smaller again?
So it's going to, so I promise you the answer when you solve this guy is going to be this. Okay.
Oh,
One
okay.
over
That term just shows up. Negative feedback, just think that negative feedback makes everything better. Okay. Negative feedback just makes everything better. And if you go with that assumption, you just you start cutting things the way that you want them to. So for example, if I open loop this guy, the input impedance was small because I look into the source, which is typically small.
Yeah.
When I put negative feedback, it's going to get even smaller. Does that make sense?
Yeah.
But the key is, what is L of S? So we have to go up here, and L of S assumes negative feedback. That's why in this stupid thing it says negative, right? So you take this guy and you say that sorry, this is my this is my okay, I'll follow what your professor says. This is my VB to VN. Yes?
Okay.
So this is my VB to VN, but therefore L of S, by definition, if this is positive feedback, I need to negate it. If it's negative feedback, I need to take the positive of it. Does that make sense?
Mm-hmm.
Or in other words, it's VN, it's always going to be negative VN VB here. Does that make sense? I just need to take the negation of it because the negation was already assumed here. So this guy's approximately negative R negative 1 over R, negative RD over RF. Does that make sense?
Yeah, it does.
That's my L of S. That's my loop gain. So in here, how are you supposed to solve this problem is that you first solve in Z in open loop. If you want the input impedance of this closed loop system, you need to find the open loop first. So I break the loop open. And what is the open loop response? It's just it's 1 over GM3, GM1. Is that correct?
Yes.
So what do you guys think Z in closed loop will be? It will be Z in open loop, and I'm going to multiply by the factor, or I'm going to divide by the factor for the circuit.
Divide by the factor because
I'm going to divide by the factor 1 plus LS, right? Which is equal to Z in open loop divided by 1 plus the LS, which is in this case, LS is equal to
negative RDRL.
negative RDRL. Yes?
Yeah.
And this guy's going to be equal to 1. This guy's going to be equal to 1 over GM1 divided by 1 minus RDRL.
RF actually.
Oh my gosh, RF. Yes?
Yeah.
And that's how you guys answer the closed loop, open loop problem. When you guys have negative feedback, yeah, you just can't do what I did. What I did was very stupid, actually. Sorry. What I did was, yeah, if there's negative feedback, you have to consider the whole thing impacting itself. So I could not just assume 2 paths because eventually these 2 paths will intersect, and then I need to consider the loop. So well, yeah, what I did was illegal. So do you guys see? I do the open loop Rn is 1 over GM. The loop gain is defined to be negative L of S is defined to be negative RDRF.
Uh-huh.
Therefore, the total is this. Yes?
Yeah.
You guys have any questions?
In case if there was a voltage source, voltage input source, then we had to multiply it, correct?
Correct. If the input was a voltage source for some reason, then the ideal guy, the circuit is ideally very high impedance.
Mhm.
So that way it takes as much of the voltage as possible. Yes?
Right.
Can you write a little cap next to it with voltage? You have to multiply.
Well, I'll be honest with you guys. My cheat sheet says it here. If the
Oh,
input
okay.
is a voltage source, you want the input to be high. If the
Oh,
input is a
cool.
current source, you want the input to be low.
Oh, nice.
Yes. If you guys ever wondered what the bottom half of this table is for, it's for this.
Hey, we used to know during midterm one. That kind of just goes out the window.
Yeah. If the output is a voltage source, you want the output impedance to be low. So notice if your input, it's opposite. Okay.
Yeah.
And the reason why you want it is if you guys want justification of why this is true, it's because you want to consider these conditions with a load resistance and a Thevenin resistance input. And then this describes, so this is, for example, in this case where your input was a current source, you assume that the input current source has a Thevenin or a Norton. Therefore, you want the input impedance into the system to be short circuit so that all the current goes down into the system, not through its own Norton.
Yeah.
Anyways, okay. Output impedance, we do the same thing. So the output impedance is supposed to be a voltage. You guys see that?
Yeah.
So ideally, do I want the output, do I want Z out to be big or small?
Big, right?
Big.
No.
Let's see
Small.
the table.
Oh,
again.
Z out. Z out.
Let's see your
That's
table.
small.
Oh,
Yeah, so 0.
Yeah.
Yes. But why? Because this guy will have a V out and it's going to have an equivalent Thevenin. This is R out. So R out is going to ruin my voltage source.
Mhm.
This is the ideal voltage source. I want R out to be small as possible so that I have very good R out. Or
Okay.
I have very good voltage. I have very good voltage drive capability output. Yes, but the table typically covers you. But I would recommend you guys work through the logic.
Yeah. I have
Okay,
sent
so-
you a picture from professors in Discord in under notes.
I see it. Yeah, that's helpful. I forgot about that.
Oh, yes. Okay. So if I wanted to make it small, first I find Z out, assuming that this guy's open circuit like this, right? I break the negative feedback, just like how in this circuit here. How did I get this? Is that I remove G and then I get back the original circuit. Yes.
Yeah.
So you remove the negative feedback portion, and then I find Z out first. So find Z out open loop. And what is it going to be? This guy's open circuit. It's the input into this. It's 1 over GM2. Yes.
Mhm.
So what is Z out closed loop going to be? So I want ideally small. So what is it going to be? It's going to be Z out open loop, and I'm going to divide by the factor, or I'm going to multiply by the factor
Divide by the factor again.
because I want to make it smaller. Correct. Okay. So this guy's going to be 1 over GM2 divided by 1 minus RD over RF. Yes? Any questions?
Good.
So that's how you handle negative feedback. Okay, guys?
I see. Yeah.
So when you guys have negative feedback, the input impedance is augmented, the output impedance is augmented, and the gain of the circuit is augmented.
Mhm.
Yes. So if you had another question, what's the gain of the circuit, right? You would calculate the gain from here to you could technically approximate it as doing this. You could take the gain, you could solve this guy for the gain, right? So you do from here to here, and then from here to here, and find the gain, and then you're gonna do this to the gain. Yes?
Yeah.
All right. Yeah, that's it. Okay.
A little bit again, how did you get loop gain equals to negative RF over RD over
Sure. So first, let's assume negative feedback. This guy clearly has negative feedback because the feedback is goes to the negative terminal. Agreed?
Yes,
And when you solve this guy from control theory, from this convention, I promise you get this,
correct.
which is 1 plus L of S, where L of S is just H times G. Yes? And that's just so if you have negative feedback, you get this. If you have positive feedback, right? Then how do you think this equation changes?
HS times 1 plus LFS.
No, it's now a negative LS.
Oh,
Because I have to basically, how can I get this guy to be acting like a basically it's as if I put a -1 here.
oh, okay.
And the -1 cancels out, and this -1 is part of G, so now it's a negative G. Does that make sense? It's just playing around with this -1.
Okay.
And if you have positive feedback, it's you positive. Okay, basically, if you have negative feedback, it's this. If you have positive feedback, it's gonna be this.
Yeah,
Right?
that's
Yep.
tight.
Where LFS is defined to be this, but it's weird because LFS is the loop gain, which is the total gain around the loop. So when you calculate this guy, this is calculating the loop gain, right? So this is the loop gain, but my definition of LFS assumes this LFS here assumes negative feedback. So for me to assume negative feedback, I have to negate it again. I'm not sure if that it's just how do I explain this? It's you're just
Is it related to the thing the professor sent with that Shockley or posted?
loop. How about this? When you guys use the term loop gain or feedback, you're supposed to assume negative feedback. Positive feedback just doesn't work. Like this circuit is fucking broken, right? So no one really assigns a name to it except broken. The name, when you say loop gain, when you guys use the word loop gain, you guys better be already paying respect to a negative feedback circuit. And because the circuit is positive feedback, okay, basically when you guys solve this circuit, okay, when I solve this guy's circuit, right? When I solve this guy's circuit, here. When I solve this guy's circuit, you actually have this. You have an H, you have a G, you have the output, you have the input, right?
Mhm.
And when you guys solve this, it was actually a plus here. And that's positive feedback. You guys agree?
Yeah,
That was our initial thing, right?
When you solve this guy, yeah, that's how we found that this guy's positive feedback. Yes. So
Yes.
this guy has this type of block diagram. You have a forward loop and you have a feedback resistor, right?
yeah,
But by convention, when you write the word L of S, it assumes negative feedback. And for me to assume negative feedback, I can't have a plus. The schematic for negative feedback has to look like this. So how can I bring this to look like this? Therefore, I can define L of S. What I will do is that I will take this plus here, which is like a +1, and I'm going to make it equal to a -1 times -1. So now I'm going to keep a -1 here, and I'm going to put a -1 here.
Okay.
So now my L of S is this. Does that make sense?
That makes
Oh.
sense, but that would
Doesn't make
change
sense.
how
It's just-
your
That's where this -1 comes from. Before you calculated this, which used to be H times G, but I want to make it L of S. I want the loop gain, so I have to, because it's positive feedback, I need to break it up into two negatives. So now I have this. So now I transfer this guy to this. I transform this guy to an H, a G, a -1, and then this. Yes. So now what's my loop gain is that it's this guy. Does that make sense? That's why I have a negative RDRF. HG was RDRF, and I negate it to get this negative. And now I can call this L of S. I'm now legally allowed to call it L of S.
Are you still saying -1 block and the G block can combine together, which makes -G, and which will change the equation again? Or on the block?
Okay.
You know you understand my question, right?
Yeah, I understand your question. Let me understand. How can I explain this? How can I explain this? Okay. You see this definition of L of S? This definition of L of S. Okay, first off, this block, the solution to this block is this equation. Do you agree?
Yes.
And what is L of S defined to be?
HFS times GFS.
It's H times G, right? Here. It's whatever is inside this area multiplied together. Agreed?
Yeah.
Assuming the outside has this.
Assuming outside has that, yes, plus and minus. like-
Okay. So let's suppose I have a positive feedback circuit, and I'm going to call this A, and I'm going to call this B, okay? And everything looks amazing. It looks so good, except it's positive feedback, right? It's like it's a 10 out of 10, but it's positive feedback, okay? Okay. So the question is, does this guy look like this? Does this block look like this block?
Nope,
Why?
because it's missing a negative.
It's missing a negative. So how can so I know it's positive feedback, but I'm gonna make it negative feedback because
By
negative
making
feedback
B
this is what I mean by negative feedback. So
Mhm.
how can I make this guy look like this guy? What can I do?
Change
making
that
B to
positive
be
to
negative,
negative.
that's how.
No, you have to make B negative and then make the node negative also.
I could also do that, right? This is equivalent. Would you agree?
Yes.
Okay, and I call L of S. So once I have this guy here, whatever's inside this rectangle, I'll just multiply it together and I'll call that L of S.
Which is A times minus AB.
Yes? Does that make sense?
That makes sense, yeah.
Okay, so now when I solve, if you're okay there, now let's say I take this circuit, right? I take this circuit, right? And I solve this circuit. I break the loop here and I solve it wrapped around town, right? And I get RF over RD over RF, right?
Right.
And I know it's positive feedback, right?
Right.
So what I have shown so far is that I have something like this, where this is like maybe RD, this is like 1 over RF, but it's positive feedback.
Correct.
Okay. So but therefore, what if I want to use L of S definition? I need to L of S assumes negative feedback. So can you modify this guy to get me negative feedback?
So yes, making 1 over RF to be negative and then changing the node sign over there to be negative.
And then now I meet the negative feedback assumption. So what's my loop gain?
RD times negative 1 over RF.
Correct, which is the correct answer.
Okay, so my question was initially when you said while you have a positive feedback, we'll have a transfer function of h of s over 1 minus L of s, right? Up there somewhere.
That was a bad explanation.
Okay, yeah, I was thinking if that's the case, your transfer function will have h of s over 1 minus L of s will be again positive.
Okay, I'll tell you this. Just don't analyze the circuit with positive feedback. Analyze it with negative feedback and sweep the negative in.
Okay, yeah, makes sense. Now it makes sense.
Okay.
I was thinking it was contradicting in the previous explanation. That's why. That's
Yeah,
all.
no, so my previous explanation was hot garbage. So just take the recent explanation.
Makes sense now. Yeah.
Okay.
Someone's gonna watch the video like and stop. Right
I
when
know,
it's-
I know, I know. Someone warn them.
There's always one person.
Yeah, I know. They're gonna take away something like I got it. All right. Anyways, is there any other question you guys want to do?
Uh,
Guys
We-
want to do
we
the
have-
midterm or something?
We have a question, G. Can you post that question that we were having a hard time with last night?
yes. How do I send this? Control C.
You could, yeah.
Let me just do this.
You guys want to do question 3 or some shit here?
This is one of the question. And wait, I'm still trying to find, okay, another one.
Okay. Wait, Shockley sent. Whoa! What the hell? People have been posting a lot of shit. What's happening? Do you want me to do this problem?
Just I was trying to do the RF thing.
Like this thing? You guys want? Is this the problem?
Just give me a second. I'm trying to upload one more.
Is that the same?
Yeah, that is one of the problem where I was trying to find the feedback factor K. It's kind of weird to me. Like it's too much. Like there are so many R's there.
Yeah, this guy's a little fucked up, but okay, let's take a look.
Just let's find the feedback factor. Otherwise, series is okay. The circuit is okay, I
I don't know
believe.
what feedback factor just means. What's the blah? What's this thing?
Yes, yes. The G of S in our previous term.
Oh, the G of S. Okay, so the input VS and the output is also voltage after the op amp. Op amp has an ideal gain, is ideal except it has a gain of A naught. Okay. And where's the output? Is this V out? And
Yeah, I assume so. That is the question.
yeah, because you can't assume feedback begins where output is.
Right. It should be there technically.
Okay, so this guy decomposes to this circuit. This is the differential input. An op amp can be modeled by this. Hope you guys know that, right?
Mhm.
This is op amp.
Mhm.
Yeah,
Okay. The VS attaches here. And then you have V out. Then you have some massive network K that feeds back to some network K that feeds back to here. Yes? Okay. Okay, that's fine. This is just a bunch of voltage dividers. I'll be honest with you. So to me,
That's what's tripping me off.
I'll teach you. Oh, you want to see voltage division? Oh, this shit's
Yeah.
good. This shit's good. Okay, here, I'll show you. Here. You want to go here and you want to come from here?
Yes.
Okay, here's what you do. You node hop, label your nodes. So this is Vx, and then you go from V out to here, then go from here to here. Yes?
teleportation, yeah.
Yep.
Teleportation. So here you go. You want V out and you want to get to Vx? Easy. All you need to do is tell me the total resistance C. So which was the top resistance? The top resistance connects between these two, and the remaining is the bottom resistance. Yes?
Yeah.
Of the voltage divider? That's how you get to Vx. Agreed?
Yeah.
Yep.
Okay, so the bottom is going to be the total resistance, RL plus RM in parallel with R2 plus R1. Do you guys see that?
Yes.
Okay, and which one are you measuring across? I'm measuring
Is
across the bottom
R2 series in R1 or R2 parallel with R1?
series. From the perspective of Vx, everything else below it. So in other words, look, if you look at Vx, I could redraw this guy as this. Yes?
Okay. Oh, so yeah, that was throwing me off.
Yeah,
So
right?
it's considering the node V minus there.
Yeah, okay, right, yeah. Did I write V minus anywhere?
No.
No, okay, so it's a voltage divider.
Oh, okay, yeah. So yeah.
Step by
Okay.
step, do not make this jump directly.
Okay.
You have to go bunny hop. Okay.
Nice.
All right. So here's Vx. Which resistor are you measuring across? Am I measuring across this top resistor or the bottom resistance?
Top right.
Fuck. What? Oh, Vx is measured with respect to ground.
Oh,
RM.
Yeah, that's a good answer. So it's Rm parallel R2 R1. Yeah. That's one. Next. Okay. Now I need to go from Vx to V minus. From Vx to V minus. So now I exactly know the voltage Vx. So how to go from Vx to here? Well, that's just a voltage divider.
Other voltage divider.
And that's just R2 plus R1. And I'm measuring across which one?
Which then would be
Measuring across R1.
Correct. To ground, because V minus is with respect to ground. Okay. How do you go from total? V minus from V out. Just multiply these two.
Okay.
Yeah. Promise you. Voltage division takes you so far.
Yeah, this is
Any questions here?
Looks good.
Yeah, that's it.
That's like 90% of the points right there. Everything else is like a point.
Hey, that's K.
Where'd you get this from? G, is this like an old test question or something?
Yeah, this is an old test question.
Like super old?
Mm, super old, yeah.
I posted the ones that were like last fall.
Yeah. So which problem do you guys want to see next?
There's one more question, Eric. And
Uh,
that's it.
and
this one.
Yes, this one.
All right. What do you need to
It's
know?
also a voltage divider again, in a way, but
What I don't even know what the
Oh.
question is.
Yeah, like what's it asking?
What do you need to know?
the
back,
gain everything.
The gain,
The GM,
Did you post
GM
it?
of the circuit.
the GM, RL.
Yeah,
Ah,
GM and
shit,
RL.
dude. I don't know how to do. Like I said, I don't know how to do that. The way Professor does it, I think his definition of GM is when V out is shorted, right? When V out is shorted,
Yeah, it is. That's
V
it.
out is shorted. Then what is the I out relative to V in? Is that right? That's his condition.
I want to say he just calls it what, 0?
I was not sure why is he asking GM. Shouldn't he be asking the AV of the circuit?
No. He's asking VAV because he wants big GM times big R out.
yeah.
Negative. That's he does two transfer functions, but how he defines each of these terms, this one's defined to be when V out is the condition when V out is 0, and R out's defined to be I don't remember, but
R out is defined to be V out over V in when V in equals to 0 again.
now your professor and I have a very different way to solve this circuit.
Okay. But can we solve it?
The way I'll solve it is different than the way your professor will solve it, and I'm not
As long
sure.
as it makes sense, it makes sense. It doesn't really matter.
G, can you just post the whole question so he can see what?
I see the question. I see the question. He
I
did.
sent
He posted. Yeah. I'm saying the way your professor wants to solve this and the way I will solve it is very different.
Can you shorthand it then, or like see, or
Oh, sure. I mean, I can. I'm just letting you guys know what I'm about to show you guys may not be.
Wait, G, sorry, G, can you just grab the whole question with the answers and just post it? I think he could probably,
No, I mean, you feel free to, but at the same time, the way I'm going to solve it, I know.
I think
I
Eric
know
already solved this question in previous lectures. I
Oh.
think I don't know, but I can show him. I
I'll
don't know.
solve it here. This guy is a common. To me, this is a common source, and this guy's a common gate. So I'm just going to do common source, common gate. So ACS here is just going to be, what do I assume? Assume no channel length modulation, so R naught is equal to infinity. Okay, so this is just going to be negative GM1 times the resistance into the drain times RD. So that's RD has RP in parallel with the resistance looking up into this guy, which should just be 1 over GM2.
Yep.
Okay, and then ACCG, so ACS from 1, and then AC common gate from 2. From common gate from 2, this guy should just be GM2 times RD.
Mhm.
So therefore, the total gain should just be this. Negative GM1, GM2, RD, RP parallel 1 over GM2. To me, that's my answer.
That's actually correct.
GM1, GM2, no.
No.
I sent you the answer though.
What your professor does is that he doesn't ask for the total. He just asks for the professor does not ask for the total answer. The total answer. Your professor asks for the individual constituent components.
One by one.
So here he assumes GM is just blah 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 blah, right? He assumes that's all GM, and then but I don't make that assumption. Like he wants you to find GM, which is not the total gain. Find R out. So okay, GM. Okay, technically GM times R out. GM times R out and mine
Right? Yeah.
it
Yeah.
should be equal, right?
Yeah.
Should be, but I'm not sure. I never did this math before. All right, let's check it. GM1, GM2, RP divided by 1 plus GM2 RP times RD. Yes,
Mhm.
that's your professor's answer.
Should
Even-
be. Yeah,
what?
yeah. That's what his answer is.
Yeah, but he should be. It should be negative. Oh no, technically it's neg. His answer for gain should be negative GM R out. That's your professor's typical. This is his form, his cheat code. I never confirm whether or not his cheat code is actually like mathematically true. So let me confirm it now. Okay, let's see. We have GM1, GM2, RD, GM1, GM2, RD. So I just need to prove that this, I just need to prove that this is equal to this, which it is, because RP times 1 over GM2. Yeah, they're equal. Yeah. Yeah. These okay, yeah, the two answers are equivalent.
Okay. I would go your way and then divide it by RD to find the GM,
Yeah.
technically.
Yeah. Yeah. R out, I agree with them. R out is just RD. That one I can agree with. So you have to find R out. Because looking down when R naught infinity is infinite, so we only have RD here.
If
Oh.
if it was if there were channel length modulation, then R out would be RD parallel R naught, correct? R naught 2.
R naught 2 plus 1 plus GM2 R naught 2 times RS2. And then you have to do everything down here. Then you find RS2. Yeah, there's a lot. It's not just R naught 2. You have to keep it amplifies RS2.
So you have to go all the way till the ground, correct?
Yeah, or until your function no longer calls another variable.
Your RS2 is RP there? Oh
No,
no.
RS2 is RP in parallel with the impedance looking into the drain, which is going to be R naught 1 plus R naught 1 plus 1 plus GM1 R naught 1 RS1, but RS1 is 0 because this is actually 0. So this guy is nothing. So yeah, it terminates here. RP in parallel with R naught 1.
Okay. Okay, yeah. Yeah, finding the R out is like really terrible when the circuit is cascaded there.
Yeah, yeah, it's not that. I mean, yeah. Once you find the R out, yeah, then you do the division. My God, it's gonna be sad. But yes, for this circuit, R out is RD in parallel with infinity.
Okay. Next thing.
Okay. Any other questions?
Looks good.
I think Josh might have had something. I don't remember.
Yes, Josh. What did you want from the final?
By the way, what time are you guys coming tomorrow to school? The library's 24 hours. Are any of you gonna get there earlier?
I'll try to, but
No.
I think I'm gonna be.
I have one more question, Eric.
Yeah.
Don't mind, please.
Yes. What's your question? Wait, no, Josh first. Maybe
Okay, yeah.
part
Oh, yeah.
2. Question 3, part 2. Find the feedback factor. So you want this circuit, Josh? Okay. I've run out of space on infinite paper. Give me a second. Okay. Okay. Let me just do a little bit of touch up and we'll be good to go. Okay. Ooh, that's gonna be ugly. All right, well, fuck it. Too bad. Okay.
That's hilarious. It's, what
Okay.
software is this?
It's some piece of shit software. It's whatever. It's some free software made by some dude, and
Did you make this software?
no, God, no. Oh God, if you guys see me programming, oh God, I'm horrible. My programming game is weak.
My Python game's strong, but C, I don't know.
Oh yeah, no, my MATLAB though, oh, I'll fucking destroy you guys. But anyways, I type of feedback amplifier What type of feedback amplifier is this? Okay, the input is current, the output is voltage, input is current. So what type of current, what type of what is this called? This has what units, guys? What units?
This has ohms,
Ohm. So which one is it?
trans impedance.
Yes, good job. Find the feedback factor and show the derivation. Well, before we do that, let's
Hey,
figure out
before
what
you,
this.
before you continue with part one, so I wrote something from the professor. Like it's finding the feedback. And actually, you know what? Screw it. I'll just send this to you right now.
Okay, well, first let's do this. Let's label the nodes. We start here. A is for apple. Which way do I go? Hello, which way do I go?
Go up towards the source of M1
Why?
because you cannot go to the drain of M2.
Correct. The drain of M2 cannot be the input. B is for bitch. C, where's C?
C is for cunt.
Yes, very good. And we go where?
Whoa, whoa, gee.
We go back to A, right?
Yeah.
Oh, very good, very good. I'm proud. Proud. Okay, and we go back to A. All right, A goes up or down. What do you guys want to pick? I don't give a shit.
Up.
Up, cool. Then from A to B is what type of amplifier?
It's not common source, so it goes up.
Oh, fuck. What I asked you
Common gate.
common gate. Does it go up or down?
Go up.
Up from B to C.
B to C is common source. That's why
Common
it goes
source.
down.
Goes
Common
down.
source. So
Yep.
C perturbates downwards.
Yeah.
Go through a resistor.
Then we just go back down.
But it stays down.
It stays. It preserves. It does not invert. And this is just a resistor divider, so it just goes down. Yes.
Feedback.
Very good. Then compare the A's.
They contradicts. That's why it is a negative feedback.
Do you guys have any questions about how to do this?
No.
Okay. Find the feedback factor. Okay. Okay. The feedback factor and show the derivation. Okay. So feedback factor, I'm going to guess is the K going backward. Correct?
Mhm.
So it's from V out
We can.
back to here.
So,
Oh, but the
yeah.
input. Okay. So this is a little bit tricky. They want the current that flows in this direction. Okay. They want the current that flows in this direction. Oh, that's a bit of a pain. That's a bit of a pain. Okay, we do it. Feedback factor. So I need to somehow convert this so through KCL they add, right? Here's IN and here is IRF, right? And together they sum to the current here. Right? That's how I do the current summation. Like if I have units of IN,
KCL, right?
what'd you say?
KCL.
Yes, KCL is what's doing the summation here.
So,
Okay, we go here, we do we go A, so you do KCL here. I just need to know what I just need to know what IRF is from V out. Because the output is V out and the input is units of what? Current, right?
mhm.
So if I adjust this guy, he has to have what units? It takes the input is voltage and the output is current, right? You guys agree? So it has units of like Siemens or Mohms or whatever you want to call it, right? Agreed?
Therefore, K has to be 1 over resistor, something like that.
Yes, exactly. Yeah, that's the unit. That's how the units of K has to work. Otherwise, I can't add this signal. The signals here are all the signals all to the left are currents, and the signals all to the right are voltages.
Sure. Yeah.
So I need to find IRF as a function of V out. Okay, so suppose I know V out. What's the KCL here? I need to know the voltage here. How do we solve this guy?
Do we break the circuit and then test it? And
I
then
think we do, but I don't know. This is a hard problem. Actually, I don't know how to do this. Let me think. How would I do this? I do want to break out IN, and then you still have this guy.
right? And we can
How
break
do
the
I
circuit,
do this?
right?
How do I do? Sorry, what?
We can break the circuit at node X and then put a test voltage there, find the thing, and then maybe something that way.
I think. Yeah, I think you're right. I find this and I invert it, right? I find the resistance looking into this path, and I think this guy's gonna be, and I think that this bottom guy, V out over IRF, is gonna be the impedance into this path, but I break the connection, right? I have to open this guy. K exists when in an open loop scenario.
Right.
So I open up the loop, I break this guy open, and I find this guy. So I think the answer is RF plus. Do I assume channel length modulation? Yes, I do. Okay, so then I have to do the impedance looking up into the source. So I think if I look into the source, I get this. I think I get that. So I get R naught 1 plus RD1 divided by 1 plus GM1 R naught 1. I think. Or if I assume no channel length modulation, this guy approximates to this.
1 hour here, maybe.
And then I think this guy's answer for the vector K is this. Is this the correct answer? Is there a solution to this? I think you guys gave me the solution, right? I erased it. For 2. Am I completely wrong? The fuck? What is happening here? K? Okay. 2t over, huh? What's 2t? 2t. That is his
That is
answer?
That is I.
Is wait.
So I of T. I of test over V naught.
That's his IF. 1 over,
What is V naught? 1 plus
1 over GM1 plus RF. 1 over 1 plus GM1 plus, hey. There's my answer. There's my answer.
Yeah.
Okay. Which approximates to RF. So 1 over, all right. I don't know how we did it, but we did it. Yeah. Okay, cool. But it's negative. Why is it negative? Let me think. Oh, of course it's negative. Of course it's negative. Of course it's negative. Because here, the current, the way RF is defined, it looks like it's adding current in this direction, right? So it's plus gets me the current here. You guys agree?
Yeah.
So I need to negate this guy twice. So then it's negative, unfortunately. Okay, that's just because he put RF this way. Realistically, if this voltage goes up, the current sinks more in here and IRF actually sucks current away this direction. So I don't know why. Okay, the way your professor put IRF implies it's positive feedback, even though it should be negative feedback. So yeah, fine, whatever. Okay, yes, does that answer your question? I guess the answer to the question is that you disable the input, you break open the loop, and yes, it's the current seen by this guy. Or it's the voltage current relationship, and I just used impedance on this open loop path. And I got this. Is that fair?
Mm-hmm.
Josh? Okay. Okay. Do you guys have any other questions you want me to look at?
Yes, there is one question on Discord again.
On what? Oh, in Discord? Oh, from Tom Hillwald. Wait, whoa. Which one?
So question number 2.
Is referencing that image?
Yes. The above image.
This one?
Oh no, not that one. Not that one. The above that one.
Oh, okay, I see.
Yep.
Okay, is it okay? Are these two things? What the fuck is this? Can someone help me understand? Is this?
Why would you fix it when you send it to him?
Is this connected?
Yes, this is connected. I think that is connected. Oh, looking at the question. Because this is a differential amplifier or differential
Okay.
circuit. So
Jesus Christ, what kind of Thano ass motherfucker? What did you send me?
He snapped his fingers and half of it
What
disappeared.
kind of fucking broken ass circuit you guys have? Okay. Okay, is this it?
Yes.
Oh my, 5, 6. So this is 6. Jesus.
The basics, yeah.
Yeah, of course it is. Yeah, I can fucking count. Okay, Jesus. Goddamn.
There is RP and another is RN. Yep. It's
Okay.
just the printer, I believe.
Huh?
Maybe the printer.
Yeah. Okay, what exactly do you guys need from me here?
I want you to do find the RP
Find RP looking up.
for signal model.
RP is just looking at one of these paths upwards, right?
We just take half of the circuit. Is that what we're doing?
Yeah. It just wants me to take half of the circuit here, right? They're both diode connected. Or sorry, no, that's not true. Sorry. These guys are common.
One is NMOS and another is PMOS.
Okay. So I call this I just reference M5, M7, okay?
Okay.
So RP is equal to one is for the source. So I go to the source area. I take this guy. And this guy is going to be R naught 5 plus RD5 divided by 1 plus GM5 R naught 5. And then I need to find what RD5 is. Okay. Is that okay?
Mhm.
Okay. So RD5 is equal to the impedance looking here, which is the drain of M7, which should be R naught 7 plus 1 plus GM 7 R naught 7 times the resistance of 7. But R7 is 0. So this guy just breaks down to this, and this guy decomposes this, and I get R naught 5 plus R naught 7 divided by 1 plus GM5 R naught 7, R naught 5. Any questions? Or sorry, maybe I should not have. I wrote this from memory. Sorry. Oops. Let me prove it to you.
Oh, that's from the common gate. Yeah. Okay.
Not the common gate. Impedances don't give a shit about what the common whatever it is. It's just what am I looking into? And I'm looking into the drain. So this is what it's like looking into the drain. So here's R naught, here's your R naught, here's your RS, here's your 1 plus GM.
Okay, makes sense. That is
Okay.
all to find the RP of the circuit
That is RP.
and finding the gain of the half circuit.
Okay, so okay. We cut this guy in half. Yes. Wait, did he ask you to find the half?
I mean, like we are supposed to half it, right? It is asking the final express for the differential.
Oh, find the differential. Okay, yes. Okay, yes. Okay, I take this circuit. Take this circuit. I cut it in half. Okay. This guy at the bottom acts like an AC ground. Agreed? Because it's differential.
Yeah.
Okay. And I'll just clean this guy up. Here's
Every
VF.
independent source act as a virtual as a ground, right? Yeah.
These all act as grounds. VB3, VB2, all these are grounded. Okay. So now you're supposed to solve this circuit, yes?
Yes.
So I could solve this my way, or you could solve it your professor's way. Professor way prefers you to say that the voltage of the circuit is negative GM times R out. In this case, GM is something which we didn't solve, but R out is just going to be RP in parallel with RN.
Correct.
And GM is going to be something, but I didn't calculate it. So which way do you want to do this?
The easiest one.
Your way, finding the AV.
Okay, my way. Okay, so I need to draw steps. Remember, A is for apple. Good. And then you have V out. Good. Okay. So first I have this guy, and then I Spider-Man swing up. So I have two stages. I have one common source on one, This guy is going to be equal to negative GM1 R naught 1. Do I assume R naught? Do I assume R naught? Okay, yes. Okay, GM1 times R naught 1 in parallel with the drain of the impedance of 1. Okay?
Impedance one. Yeah,
Yes, that's the because there's no RS, so I eliminated that last term.
makes sense.
Yeah, I got rid of this term. I just took these two. Okay. So I took RD. So RD1 is equal to the impedance looking up into the drain. This is going to be a long time running. So here we go. So RD1 is going to be the impedance looking into the source. If I look into the source, I will have R03 plus RD3 divided by 1 plus GM3 R03. You guys remember that loop gain factor that we talked about before, by the way? Remember how we said like divide and multiply by this? 1 plus blah, 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 blah.
Yeah.
For MOSFETs, the loop gain, if you guys look at my expressions, I always batch together the 1 plus GMRO everywhere. This is very intentional because I actually have been paying respect to this loop gain idea. Okay, so like this 1 plus GMRO is like a bonus factor. Okay, maybe not for this one, sorry. This one. It's that extra factor. I put it everywhere because it does belong there. That's what a MOSFET does. A MOSFET effectively enables you. So when you look into the source, right? The source is supposed to be a low impedance. That's why you divide by it. Anyways. Okay, so here's RD3. Okay.
We're looking at the source, that's why the impedance is low, that's why we divide it by that factor. Is that-
Correct.
Okay, makes sense.
That's how I have it memorized. Okay. And this guy is the drain of this guy, which is just RP. Luckily, we just solved that. So I'll just grab it from here. Okay. Any questions here? This is now entirely ACS 1. Now I need to do a common gate of M3. And that's just now GM3 times something. I'll just use this form, whatever. Oh, shit. I'll use this. So this is GM3, R03, R03, RD3, RD3. Luckily, RD3 is already found, so I don't have to do any more. Okay? So the total AV from V out from V in is going to be equal to negative GM1. It's going to be negative GM1, but then I'm going to expand this guy out. RD1 is going to be this. Okay. But RD3 is going to be this.
Volume.
Okay. And then this guy is going to be multiplied. This guy is going to be multiplied by this. But RD3 is going to be RD3 is going to be multiplied to this. Okay, any questions? It's a bit nonsensical, but yeah. So this is the area where it looks super messy and your professor's probably gonna like hate you. So this is where your professor's method does have merit. I just never checked whether or not your professor's equation is precisely mathematically equal to this one.
Wow.
That is a long ass equation.
Where do you find these complicated questions? Is this like all passing jams?
This was one of the final.
For like a couple years back or recent?
Yeah, a couple years back.
Was it the same professor teaching it?
I am not sure.
But this is a legit question because we did something like this to
It
another.
covers everything like differential equations.
This was like, I think homework. I remember one of these in like the homeworks.
This
but-
circuit he's using for explaining all the concepts, but he always use one generalized equation for this, like
Yeah.
finding the gain. Like R up parallel, RP parallel Rn, and then he goes with that. That's all. But he doesn't really simplifies for RP parallel Rn. So
Yep. So, any other questions?
I have a questions regarding the body plots.
Okay.
Mm,
Please feel free to refer to the other Discord where I go through many body plots example. Wait, from a transfer function or from what?
no, generally drawing the body plots and then like and then determining the stability of the
Oh, I know what you're
guess-
talking about. With the poles and the zeros,
You guys need that?
with the phase and the
yes.
If there's only
These are
one
my
zero-
questions actually. Yeah.
Did you do this in you're in 133 right now, right? Or 132? Have you done this yet?
Yeah, we do, but
Yeah, he does it way more in depth than we did in 110.
I mean, what happens if there's only 102 poles? I mean, if I
No.
understand correctly, he's gonna want you're gonna have a you have a bandpass filter.
And,
Yeah.
Yes, the bandpass filter frequency as well, even.
Yeah. Oh, sorry, what?
I was asking, what if there is only 1 0? What if there is only two zeros? What would be the
Fuck.
body
Okay.
plot?
I mean, that's wild, but yeah. Like that?
Question was, what happens when there is only 1 0?
Okay, like this.
Like straight line or
Yeah.
just 1 0? 1 0.
How about this? 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 Here, I'll teach you both real simple, real simple. Okay. Okay. You start at DC frequency and the frequency goes up to infinity here. Okay.
Yeah.
Okay. That's your x-axis.
Mhm.
Now, a pole is like a landmine. You lose $20. A zero is like you pass go. You get $20. Okay. Is that fair?
Okay.
Okay. So now here's what happens. Suppose I start pole, zero, pole, right? At some frequencies, I start left to right, and let's say you start with, let's say, $10, okay? Or no, sorry. Let's say you start with $0. I pass a pole. What's my new amount of cash I have on wallet after this point? So from here to here, how much cash do you have as you walk from left to right?
-20.
No, from here to here.
0.
You start with 0, okay? Then from here to here, what do I pass this point, and what do I have now in my wallet?
Plus
-20.
-20.
-20. And then I pass this. What do I have in my wallet?
0.
0.
Then I wash it, and I pass this,
-20.
20.
and then I pass this.
-40.
Okay, these are the slopes. 0, -20, 0. It would be 0, -20, 0, -20, -40.
Okay.
So if you have more negative, the slope is now -40 dB per decade. Does that kind of make sense on the magnitude side?
Yeah.
So when you guys said you had 1 0 and 2 poles, it would be here, up, over, down. Unless the 0 is all the way at 0, then if the 0 happens all the way at DC, then you start off with $20.
Yeah, that was my initial question. Like, what happens when there is like when you have a transfer function like 3s plus 1? That's all.
3s plus 1?
Or 3s.
3s? Yeah,
Yeah.
3s, then you have a 0 at 0, and you just have you have a differentiator, and you always are positive 20 for your entire life.
Okay. And yeah. So and when you have like 2 zeros, then it will go from 1.10 to another to 20, and then from that point it will go to 40, right?
Yes.
Okay. Yeah. So that was my question for the first one.
Yeah, this is a low pass filter. What happens when there are two poles? This is a second order low pass filter. Like boom, boom, ba, 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 right?
Makes sense.
What happens when there are two poles, two zeros? And you will have a nice clean, like this is called a shelving filter.
Do 110.
Unless the two zeros happen first.
Yeah,
If two zeros happen first, then you go up, and then you have two poles, then you have a high pass filter, possibly. It depends where they're located.
Okay.
dang, dude. If that was one of the questions, I'd be so happy.
There is a question. I think it's on the question where Sanjit said it, where he asks for the stability, finding the margin and then finding the stability of the circuit, I believe.
Yeah, he did mention something about stability margin.
Let me find
Or
it.
like overshoot factor, something like that as well.
So we're sorry, is there another specific question somewhere, or?
Looks like you have covered what we had.
Yeah, I'm like well prepared. I just have to.
Okay. Is there anything else you guys want me to go over? Otherwise, we're good.
I'm good. Are you guys okay?
I had one more question. I'm trying to pull out from the lecture notes.
Okay, Josh. Oops. Oh my god, I just combined names. Josh, Justin, or Ron. Do you guys have any questions you would like to go over?
Yes. Is one of them
Yes.
the homework?
Oh, okay. What about the homework?
Oh no, it's one of the questions that you solved earlier for one of the homework.
A lot of them are from the homework. I recorded it. I'll post it up. So we
Right,
did that
let's
earlier.
see. Okay.
Yeah, we did we did homework 5, question 1. The first 2 questions and the last 3 questions. So I think we did questions 1, 2, and like 7, 8, 8, 9, 10.
Okay. Yeah, for like say 12, 22D for homework 5.
12, 22,
For the part C.
part C. No, 12, 22. Huh? This one?
Yeah.
Oh, we did not do this problem. Would you like to do this problem?
Yes.
All right. You guys ready to say your alphabet again? Here we go. Here we go. All right.
And this is easy. Looks like this is easy.
All right, Justin, you ready?
Yes, sir.
All right, here we go. All right. So we start VN. Where's the next node that you want to label? Oh, do you know my method?
He does not. He just came.
Oh, shit. All right, man. Take a look. Okay, we start here and we have to somehow get to V out and come back. That's how feedback works. So we have to start inching, and every net like you do for KCL, you have to label. So we start VN, so we start here and we're gonna get here, and this is now A, yes?
A for apple.
A for apple.
I see the node. Yes.
Okay, now which way do you go? Down, left, or up?
Let's see. I think I would say up.
Okay, suppose you go up. You're considering for this MOSFET, you're going into its drain, source, or gate.
Let's see. GT.
Right.
Strain.
It's drain. So you're considering the drain is as its input. Is the drain allowed to be an input for a MOSFET?
No.
Oh wait. I see.
Yes, that's
No.
illegal. That's very illegal. So which way would you like to go next?
M1.
Ah, beautiful. And we get to out, right? And we'll call that B. Okay. Is that agreed?
Yes, sir. Yes.
Okay. And then we go from where to where? B back to. You want to get back, you want to finish the loop as fast as you can. So you go
B back
A.
to
And you
M2.
go, you're going into what of M2?
the source.
And you're going out of it.
It's a drain.
Is that illegal?
No.
A. Read the question. Don't read my tone. What's the? Are you allowed to go into the source and out of the drain? The answer is yes. That's a common gate configuration, actually. So the rules of thumb, Justin, are very simple. The gate can never be the output, and the drain can never be the input. Everything else is legal. So here, the source was the input, and the drain is the output. Does that break any of the rules?
Nope.
No. No,
Nope,
it
it
doesn't.
does not. Therefore, this is a legal path. It's called a common gate amplifier. Okay.
I
So
see.
I have A to B to A. So when I go from A to, okay, so first let's perturbate A up or down. Pick a direction. I don't care.
Up.
Sure. A perturbates up. What's the relationship from A to B going forward? We go through M1. So what type of amplifier is this, Justin?
That will be a drain, voltage drain.
Sorry, one more time. Common what type of amplifier stage is this?
Source drain.
Source to drain. Wait, it's like source to drain?
Gate.
Did you mean to say gate, Justin? Because this is gate, the signal comes from gate to drain,
Yeah, basically gate drain.
which means which terminal is not being used?
Source.
The source. So we call it common source because the source is not being used. Okay, and is common source inverting or non-inverting?
It's a non-inverting.
Oh, be careful. If you look at common source, the gain is the only one of them that has a minus. So it is actually considered to be inverting. Is that fair?
Yes.
Okay. So this guy's inverting. Okay. So if it inverts, if A goes up, what happens? If the signal A goes up, what happens to B? Does it go up or down?
It goes down.
Correct, because of the inversion. Now from B back to A, it goes through what? It goes through which MOSFET?
The M2.
M2. And input, and what type of amplifying stage is it? In other words, which terminal is not being part of the which terminal is not part of the signal path?
Common. Let's see, source.
Common gate.
Yeah, because here the signal is touching the source and it's touching the drain. And the terminal that's not being used is the gate. So you call this common gate. Does that kind of make sense, Justin?
Yes.
Okay. And do you know if common gate is inverting or non-inverting?
It's a non-inverting. It's
It is
inverting.
non-inverting.
Yeah.
Sorry, what'd you say?
Non-inverting.
It is
It's
non-inverting.
non-inverting.
So if B goes down, what happens afterwards? If B
It
goes
stays
down,
negative.
it stays negative. Okay. And now have you reached back the same point? Yes. So you look at the two and you tell me, if they're in disagreement, they are invert. This is a negative feedback. If they are the same, then they are in positive feedback. So is this negative or positive feedback?
Let's see. Negative feedback.
Correct. Okay. We go to this example now. So here you label the node. You call this guy A for apple, somewhere in the loop. And which way can I go? Up to the right or down?
Let's go down. What do you say?
But I don't know. If you go down, I would ask you, where do we go next? Yes, which way can we go? Which way can we go?
You can only go up.
So if I go up, okay. If I go up, I go into what of M2?
Then you go into the drain. So that's
Okay.
no.
Yep, illegal, correct.
So we have to go to the M1
Correct. And I go into its,
source.
and the signal leaves out of its
Drain.
drain. So therefore you call this amplifying stage common
Gate.
Correct. which is inverting or non-inverting.
It's non-inverting.
Correct. Okay. So we go here, we call this B, and then B, we go back down to A. So from B to A, what is it?
The B to A, that's basically non-inverting.
Wait, first I go into its
What is the gate?
and I leave out of its
Through the drain
drain. So therefore it's called a common,
source.
and therefore is common source inverting or non-inverting?
It's inverting.
It's inverting, correct. Okay. So we go A to B to A. You just said A to B to begin with is a common gate, and the next one is a common source. And you want A to start up, going perturbate up or perturbate down?
A is up.
All right, sure, whatever, doesn't matter. And then common gate is inverting or non. So now does B go up or down? And tell me why.
So it goes up since it's non-inverting.
Correct. And then back to A.
It's a negative. So they're just common source being inverting.
Correct.
Why?
And therefore, if you reach the same spot, you look at these, and what happens?
It's a negative. You get a negative feedback.
Correct. All right, correct. Any questions about that question, Mr. Justin?
No.
Yep, very good.
Solid work, Eric. Thank you. Does anybody else have anything? So I can like.
I want to talk about the phase, margin, and crossover frequency.
Okay. This is going back to control theory. But yes, this is phase margin. Yes. You need some phase margin.
Yeah,
Wait, you have to understand this?
a little bit. Like I kind of understand it where you're
Oh, this is
CFS.
hard. This is a very interesting. This is a very good subject. Very important for power systems. Actually, very important in control theory in general, actually, any negative feedback circuit. But it is a little bit. Will you be tested on this?
I think so.
Oh, okay. I would say 60 degrees phase margin is good enough. It's the distance away from 180. And there's phase margin and gain margin here, actually. But basically, the bottom term, you see this? What's the worst thing? What's the worst thing for LFS to equal for this thing, the whole thing to blow up? What can LFS not equal?
-1.
-1. What is -1 in phasor? It's one. It's a magnitude of 1 phase.
-1 is what?
-1 on the complex axis. On the complex plane, -1 has what magnitude and what phasor? Vector, damn it. If I have a vector and I have the point -1, this vector has what magnitude? How long is this vector?
1,
And what angle does it have?
180 degrees.
All right, I'm gonna just choose -180 by convention. Okay.
Yep.
So this is a very danger point. This is a massive danger point. I do not want LFS to ever hit this point. Ever. Otherwise, that's very bad because if this is -1, that's equivalent to what? That's equivalent to positive feedback.
Oh, okay.
Yes. So I want to avoid this point. So in magnitude scale, where does this land? Where does this point live? On the magnitude plot. Magnitude is when this guy is at what dB? Linear 1 is at what dB?
Log of
Good, 0 dB is a good answer. So you have 0 dB, and I want the phase. If this is 0 degrees phase, I want to avoid being anywhere close to 180. Okay. So when my transfer function, let's suppose I had a transfer function that looks like this, okay? Right? Something like this. The moment my magnitude touches 0 dB, my length is 1. I want to make sure when my length is 1 that I do not have an angle of 180, a phase of 180. So it's the distance away from 180. This is the blow up point. It's the distance away from 180 that is called my phase margin. Does that make sense?
distance from 180. Will it come from there? Okay.
The moment that my loop, I'm plotting LFS. LFS could be something, whatever the fuck it is. I plot it.
And the moment I intersect 0 dB, I check to make sure the phase is nowhere near 180 degrees.
Okay.
Because that would be positive feedback at that frequency, and you get oscillation. So if you look at this guy, you see the moment the magnitude plot touches 0 dB, you see?
Mhm.
You check the phase, and you see the phase is equal to negative 180, right?
Then
Which
the
means
phase-
at this frequency, the phasor is one phase 180 degrees. This means oscillation at this frequency.
Okay. But it can be 0.5 negative 180 degree, right?
0.5 dB?
Uh-huh.
Yeah, that's going to be fucking marginal, but yeah.
No, just for example.
Wait,
purpose.
no, it can't be. No, it has to be less than. Sorry, no, you can't. No. Because if you assume decreasing, if this is 0.5 at 180, when you're at 180, you want the gain to be, when the moment you hit 180, you want the gain to be less than 0 dB. Otherwise, you're
Oh,
going to amplify. If it's higher than 0 dB, you're going to amplify the signal as you go around the loop or loop. So that's also very dangerous. You want like negative 20 dB or negative 10 dB. That's called gain margin. But we're only focusing on phase margin. So you see here, this is the unity gain frequency, right? This is when the gain is equal to 1, linear. You check the phase, yes? And you want the distance away from 180 to be big. Here it looks like it's about 30 degrees, okay?
oh.
Here, when the gain hits 0 dB, the phase margin is about 60 degrees, right?
Oh, okay. That's why we need phase margin to be 60 degrees. Okay.
And then you usually get this whole system responds pretty cleanly. And in this case, if you have very low phase margin, you tend to be more unstable, which is why you see ringing. And if you have no phase margin, you for sure blow up. You oscillate. That's guaranteed.
Okay. Makes
And
sense.
it all comes from the fact of this guy right here. Does that make sense?
Right, makes sense. But we generally have a phase margin of 60 degree to have a clean.
Yes, you will find that standard in industry, especially automotive. Automotive will require any negative control feedback system. You have to be able to measure its feedback to be 60 degrees phase margin. That's very common in automotive platforms. That way, when the part typically 45 degrees is a sweet spot optimal performance where you have really fast, clean step response with minimum overshoot. 45 degrees is a sweet spot in most systems.
Okay.
But this is a rule of thumb because remember, phase margin, gain margin, all the shit only applies at one frequency. The rest of the graph can be really dumb, right? Right? It can look really dumb, which changes the whole performance. So this is more of a rule of thumb.
Okay.
Okay. In terms of like what number you should aim for, 60 degrees is pretty common in industry. As components age, as your car ages, as your rocket ages, as your satellite ages across like decades, typically the phase margin tends to decrease, but within like 5 years, it still goes down to like 40 or 50 degrees, and that's still more than stable.
Oh, that's why we make like industry make 60 degrees.
You margin up by design. Yes, this is very common in if you have a project that has a long lifetime, you typically will see 60. If you have a consumer product like your phone or something, things that are supposed to be technically disposed of in like a year or two, 40 to 45 degrees to 55 degrees is accepted in industry. But this is a very potent topic. Actually, this would probably be one of my interview questions.
Okay.
If I were to ask, this is a very powerful topic in control theory. I strongly recommend you guys understand it.
Yeah.
Thank you.
Yeah, that is
Okay.
all. Yeah, thank you, Eric. It's really appreciated.
All right, guys, we can end the recording here.
And
right.
do you mind putting that your little table on the notes too? Like the downer table.
Oh, yeah.
Please.
Okay. All right, guys. Yeah, that's the end. I hope you guys enjoyed the material. Hope it was fun. Yeah, just hope you guys really like electrical engineering.
Yeah, I would love to take you on dinner.
No.
All right.
I'm pretty damn sure I emphasized my rules at the beginning. you guys are not allowed to pay me back. You can only pay it forward. Teach someone else, help someone else, not me. I don't need it. I promise
No,
you.
dude, when I see you, man, I'll buy you lunch.
Yeah,
I'm
no,
running into you.
I'm gonna say.
Oh, I really personally want to meet you at like in
Yeah,
a
I'm
bar.
sure I'll run into you, bro.
Get wasted.
I hear
Get
what you guys
wasted
are
with me.
saying. I'm picking up what you guys are putting down, but I'm gonna say no. I'm always gonna respectfully decline.
Because I have friends in Seattle. I can come visit.
I fight on San Jose more than enough. It's
Yeah.
fine. But it's okay, guys. Thank you so much. Is this your guys' last semester for this, or
Yeah, for this, yes.
no? I mean, like for SJSU, or
For some,
Um,
for some.
For my buddy
have one
Ronald,
more.
Ronald's graduating. This is his last semester. Ronald, congratulations.
yeah, goddamn. Best
The
of luck,
rest
man.
of us, I think I have like 2 more.
Got it.
Yeah.
Got it. Got it. All right. Well, if we happen to cross paths on another course, just let me know.
Oh, we will, dude. I'll keep in contact.
Okay. Also, if you have the younger generation of SJSU, I do expect to continue offering this to SJSU folk.
Yeah,
So-
I'm gonna pass this Discord on to the next semester.
Yeah. Sounds good. Feel free to introduce me to the younger guys.
I will, man. Thank you so
All
much.
right.
man.
Thanks, Eric.
Take
Take
care,
care.
guys. Bye-bye.
All right, good luck, guys.
Bye-bye.
See you guys tomorrow. Come early.
What time is the test tomorrow?
It's at 9:45, but I'll be in the SJSU library at like 7. So just like it's open 24 hours.
Oh, okay.
Yeah, so just come early.
Yeah, we'll see. Because yeah, okay.
All right, man. Bye, guys.